Welcome to my talk. I'm HyungSeok from Theory. Today I'm going to present a precise and scalable detection of use-after compiling garbage collection bugs. This is a joint work with my colleagues Andrew Wesie and Brian Park. Garbage collection is a common method for automatic memory management. It finds and reclaims dead memory objects that are no longer used in the program execution. It is used extensively in web browsers to manage their memory objects, as well as dynamic language runtimes like the Microsoft Common Language Runtime for .NET. Let's review how simple garbage collection works. Assume that 5 objects are allocated and managed by the garbage collector. First, the garbage collector figures out which objects may still be in use in the rest of the program execution. Weaker objects that are still in use as live objects and refer to objects that are no longer used as dead objects. Then the garbage collector frees the dead objects. However, this simple garbage collector is not efficient because it causes memory fragmentation. After dead objects are freed, they leave behind memory holes. If future memory allocations are larger than the holes, new memory must be allocated and the holes remain unused. To mitigate the memory fragmentation problem, we can use compiling garbage collection. The basic idea is to remove holes by moving the live objects. Let's start with the previous memory state, but now assume that we use a compiling garbage collector. After the garbage collector frees the dead object, it rearranges the 2 live objects to remove the holes. Next, the garbage collector needs to update the references pointing to live objects that were moved. To update the references to the live objects, the garbage collector maintains an address table that contains memory addresses where the references are stored. We refer to pointers in the address table as rooted pointer, and we refer to pointers that are not registered in the address table as unrooted pointers. So during garbage collection, the dead objects are freed and live objects are rearranged while corresponding rooted pointers are updated. The unrooted pointers to moved objects become dangling pointers because the garbage collector does not know about them and will not update them. Therefore, there will be a use-after-free bug if an unrooted pointer is used after compiling garbage collection. We refer to this bug as a use-after-compiling-gc bug or use-after-cgc bug. A use-after-cgc bug requires a sequence of an unrooted pointer definition, compiling-gc invocation, and use of the unrooted pointer, which we refer to as def-cgc use. If there exists a feasible path for def-cgc use, we can conclude that there is a use-after-cgc bug. Thus, finding use-after-cgc bug is the same as finding feasible def-cgc use pairs. Use-after-cgc bugs have been found in real-world software. Here is a use-after-cgc bug in Google V8. First, an unrooted pointer named code is defined by a call to get bytecode array. Then the getParameters function internally triggers a compiling-gc. And code becomes a dangling pointer because compiling-gc may move the objects that code referred to without updating the code. Finally, code is used as a function argument, and this leads to a use-after-cgc bug. To detect use-after-cgc bugs, Google V8 and Mozilla SpiderMonkey already employ a static analysis tool named gemole and rootAnalysis respectively. From the source code's abstract syntax tree, they first calculate call graphs and enumerate functions that trigger compiling-gc. They then find def-cgc use pairs by traditional data flow analysis and conclude them as use-after-cgc bugs. However, traditional data flow analysis may miss data flow through memory, so some use-after-cgc bugs are not found. Additionally, these tools do not check whether def-cgc use pairs have feasible paths, which may lead to false positives. To mitigate false positives, they maintain a list of non-compiling-gc functions and filter these out of the list of enumerated compiling-gc functions. They also ignore use pairs that are in the scope of no-distance annotations, which the developers manually add to the source code. This heuristics makes the prior tools scalable but path-insensitive. And the heuristics are tightly coupled with their targets, so they cannot be used to detect use-after-competing bugs in other targets. Our goal in the paper is to design a use-after-cgc bug detection tool that can address all the challenges that I have mentioned so far. Specifically, we want to design a detection tool that can support multiple targets and systematically find use pairs and check their feasibilities at scale. We propose a new use-after-cgc bug detection tool named CFG. CFG has two modules, a detector and a checker. First, based on the LLMIR, the explicit competing GC function, and the memory cell type of the target program, the detector module collects a set of unrooted pointer types and GC functions. In this step, we only use curve graphs and type graphs without any target-specific heuristics so that we can support multiple targets. Then the detector module performs static symbolic taint analysis while traversing the reduced CFG to systematically find use pairs. Lastly, the checker module performs directed symbolic execution while traversing the directed interprocedure CFGs to check the feasibilities of detected use pairs. Let's take a look at how the CFG reduction and static symbolic taint analysis work. The primary goal of CFG reduction is to remove nodes and edges irrelevant to use pairs so that analysis is faster. We find which nodes define or use unrooted pointers by checking whether theory instructions define or use unrooted pointers typed values. So we also find nodes that may trigger competing GC functions based on the list of the GC functions. In this graph, we assume that CC prime internally triggers CGC. Finally, we get the reduced CFG by removing nodes and edges that are not in paths from the function entry to def node, from def node to CC prime node, and from CC prime node to use node. Based on the reduced CFG, we perform static symbolic taint analysis that intraprocedurally tracks a data flows of unrooted pointers by symbolic evaluation. This employs type-based taint policies and ignores path constraints because the checker module will handle it later. As a result, the detector module successfully finds a def-CC use pair in the example. Next, the checker module checks whether the detected def-CC use pair has a feasible path or not. Before diving into the directed symbolic execution, the checker module constructed the directed interprocedure counterflow graph. It optimizes the ICFG by removing nodes and edges irrelevant to checking feasibility of def-CC use pair. First, suppose that the previous CFG expands to this ICFG, and the CC prime function internally triggers the CC function at this node. In this ICFG, we can reduce nodes and edges that are disconnected from the CGC node because a feasible def-CC use requires a call to the CC function. After reducing the ICFG, we can discover constant constraints with a symbolic execution. For example, to reach a use X node, the value A must be 32, so we propagate the constant constraints and optimize the ICFG. In this example, the constant constraint A equals 32 propagates into CC prime functions, like this. As a result, we remove the edges with the constant constraint A not equals 32 and the corresponding node. Based on the direct ICFG, we perform interprocedure and under constraint directed symbol execution to check feasibility of def-CC pairs. To be more scalable, we also prioritize path traverses using direct scheduling. Please refer to our paper if you are interested in the details. So this is how CFG works. Now I will show some evaluations on our system. We evaluated CFG on Google V8 and Mozilla SpiderMonkey. We passed their memory cell types and compact juicy function into CGSAN. We also set timeouts for static symbolic taint analysis and direct symbol execution as 10 seconds and 10 minutes respectively. As a result, the detector model totally found 1,484 depth-use pairs in 71 minutes while having 230 timeout cases. We also showed that with the CFG reduction, the detection time decreased by 40% and timeout cases decreased by 48%. This highlights that the CFG reduction makes the detector module more scalable without any additional false positives. Among 1,484 depth-use pairs, the checker model found 18 feasible depth-use pairs and verified 1,309 infeasible depth-use pairs. In addition, after using the directed ICFG, the checker model detected twice as many feasible depth-use pairs and significantly more infeasible depth-use pairs due to fewer timeouts. This showed that the directed ICFG improves scalability of the checker module while preserving precision. Finally, we triaged the feasible depth-use pairs by their function names and got 15 unique bugs. If you are interested in more details about this, please refer to our paper. Of course, our system has some limitations. First, we assume that compiling GC must move all unrooted pointers, but there exist some unrooted pointers that are not moved even after compiling GC. Second, we can handle compiling GC triggered in other threads. Finally, we tried to mitigate the path explosion problem with directed ICFG, but it did not completely eliminate the problem. We leave overcoming these limitations as future work. Lastly, please refer to our paper if you are interested in more details about these items. This is the end of my presentation, and thanks for listening.